Hello and welcome to another LeetCode problem. Today we're going to be doing the problem of the day for July 2nd, maximum number of achievable transfer requests. So in this problem we have n buildings numbered from 0 to n-1. Each building has a number of employees. It's transfer season and some employees want to change the building they're in. And you're given the requests where the requests from I represent the employee's request to transfer from building I to building I. All buildings are full, just like, tech companies these days. So a list of requests is achievable only if for each building the net change in employee transfers is 0. That means the number of employees moving out has to be equal to the number of employees moving in. So let's figure out the maximum number of transfer requests. And so we can actually draw this. So let's just say this is building 0, building 1, building 2, building 3, building 4. And so there's one person that wants to go from building 0 to building 1. So there's one person coming in there. From one person wants to go this way. So obviously this is going to be able to be handled because that's just 1 to 1. Now so let's actually get rid of those and we can say that's 2 requests already. Now there's another person that wants to go from 0 to 1, then from 1 to 2, then from 2 to 0. So this is it's straightforward as well, right? Like you see these 3, it's obviously possible. And let's actually leave those other 2 in here. So one wants to go here, one wants to go here, and wants to go from 3 to 4. Okay, so from this picture, you can see that from 0, 2 want to leave and 2 want to come in. And so that's pretty straightforward. From 1, 2 want to leave and 2 want to come in. And then from 2, 1 wants to leave and 1 can come in. And then from 3, 1 wants to leave, but no one wants to go there, so we can't fulfill this request. So we can fulfill every request other than that, giving us 5 requests. Okay, let's go to the next example. So here we have 3 buildings. And someone wants to go from building 0 to building 0, so obviously that can happen. And then someone wants to go from building 1 to building 2, so obviously that can happen. Or actually, not obvious, but someone wants to go from here, someone wants to go from here. So here we can handle every request because 0 has 1 person coming in and out, and then each of these has 1 person coming in and out. Okay, let's go to example 3. So we have 4 buildings again, so 0, 1, 2, 3. Okay, so 0 wants to go to 3, 3 wants to go to 1, 1 wants to go to 2, and 2 wants to go to 0. And so if you can see here, in every building there's 1 person coming in and 1 person coming out, so all 4 requests can be handled. So while this looks like a graph problem, this is actually, and once again, the big hint is these small constraints. Small constraints, hard problem, probably going to be a really bad time complexity algorithm. They're not going to be a hard problem with small constraints that you can solve in like n squared, right? That would be pretty nuts. And so what are the worst algorithms we know in time complexity? Where there's a good old backtracking, which is pretty much a brute force solution, right? And so for backtracking, first of all, we got to recognize the states. Like, how do we actually know that requests can be handled? Like, once we try a bunch of requests, how do we actually know? And so they tell us that the net change in employee transfers is 0. So what we can do is, going back, we can actually make an array for every building. So here there's 5 buildings. We can set these all to be 0. So for every building, we just set the net change. And then for every request, we just update these numbers. So we update them back and forth. And then our base case is, once we've went through every request, if all of these are 0, that means whatever request we chose to do can happen. And then for each request, we just say, try it, try a request, and then don't try the request, try those states. So now we need to figure out, like, what are going to be our return variables to make sure this works. So it's pretty straightforward. If we have this state in our output, we can return 0 because that's a valid output. And then if we have any other state, like let's say we have a state like 2, that means this output, whatever request we chose in our backtracking, is not valid. And we want to make sure that we never take that solution. So we can just return negative infinity. And that's like a nice way of doing it because we're trying to maximize our number of requests. So if we just return negative infinity for every state that's invalid and 0 for every state that's valid. And how do you know a state's valid? once you actually are done with the request, you need to check the array, and you can just check for the maximum in the array, and the maximum needs to be 0. Because if there's something that's like -2, this is a zero-sum game, right? Like you're subtracting from one and adding to another. So if something's -2, then something else is going to be 1 or 2 or whatever. So for any negative number, there's going to be a positive number. We can just check for the max to be 0, and if the max is 0, that means this whole array is 0. Okay, so that's going to be our algorithm. We're going to go through the request. We're going to see, let's try with the request, let's try without the request. And our base case is when we went through all the requests, is the net change in every single building 0, and that means we have a valid solution. Okay, so pretty straightforward backtracking. So we can also try to add the, because this is such a small amount, we can also try to add the optimization that we saw here, that if the request is from one building to itself, should we always allow that? And the answer is yes, right? Because the net change there will be 0. So if the request is from the same building, we can just say, let's just let it go, and let's move on to the next building. We'll always allow those. Okay, so let's code that up. So we're going to make an array of the net requests for each building, right? So that's going to be 0 times n. Okay, now we're going to make a backtracking function, so we're actually going to call it turtle speed, because that's about the rate that these things go. One of the worst functions to use in terms of time and space complexity, so let's call it that. Now what are we actually going to take in? We just need to take in an index in the request, all we need. Now let's check for the base case, right? So if index equals length of requests, what are we doing? We need to check for the maximum in net requests and make sure it's 0. So if max net requests equals 0, and this doesn't cost us much because all these are like 20, 10 elements, you know, so on. So if the maximum is 0, we can return 0. Otherwise, we can return, yeah. We can actually just reword this to make it a little bit cleaner. So we can just say return 0 if max net requests. Doesn't hurt to make it a little cleaner. Equals 0, else return this. Right? There we go. Okay, so now that's our base case. Now we need to handle the other case. Pretty straightforward. So we're going to make a result. We're going to make it -infinity because we're trying to maximize it, but we want to make sure that in the current state of cases we're in, we can even have a valid output. And so there might not be a valid output, so we need to initialize it to -infinity just to make sure that that is the case. And once we call this function, originally there will always be a valid output because we can just do nothing, right? Like that's always going to be a valid output. But in some recursive case, there might not be a valid output. Okay? So now remember that if the request, so we actually need to get the request, right? So let's just do that as well. So from where and to where is going to be the request. So that's going to be the request. Now, if from where equals to where, let's do our little optimization, right? Let's just move on to the next one because we're always going to take that request. And if that's the case, we don't have to update our net request because we'll just add 1 and subtract 1 to the same thing. So we can just say res plus equals, we can always add it because this is always going to be the better case to do. Actually, we can just return straight away here. So we can just say return, because this is the only thing we're going to take. We're going to take return 1 plus, this should work, I think, turtle speed. Like, there we go. Okay, because like we're always going to want to take this request if that's the request. Okay. So now, oh, actually, this shouldn't be 1 plus. This should be res plus 1. Because we can still be in an invalid state where even though we want to take something, okay, there we go. Now, otherwise, so what do we need to actually do for this backtracking? So we need to leave from the building that we're leaving and go to the building we're going. So we need to actually, our net requests from the total employees, maybe that's a better name, but the total employees at building from where is going to go down and to where is going to go up. So let's do that. So it needs to be net requests. So yeah, I think net requests is not a great name, but we have what we have. So net requests from where, it's more like total employees at the building is going to go down. And now wherever the person that's going is going to go up. So net requests to where is going to go up. Okay. And so now that we actually accepted the request, let's maximize our result. So result equals maximize. We're trying to always maximize our result. So if we took the request, it means that we did take a request. So we need to do 1 plus the recursive case. And so that's going to be turtle speed at index plus 1. Okay, so now, of course, backtracking. So we tried to do something. Now we got to backtrack out. So we're just doing this code in reverse. So now we subtract from here. Then we add to here. Okay. And so now we do have one other check, and that's if we didn't take the request. And so if we didn't take the request, then our result is going to be the maximum of just this next recursive case where we change nothing. So in fact, we could have even done this earlier, but we wanted to check for this first. So, okay. So this is if we didn't take the request, we made our net request go back to what it previously was. And if we don't take the request, all we do is just say the result is the maximum of the result and the next index because our request wasn't taken. But if we did, then we have to add a 1. That's what we always add a 1 when they're the same. Just slight a little optimization. Always helps in backtracking because backtracking is so terrible in time efficiency. So now let's return the result. And now finally we can just say return turtle speed. And we're going to start at index 0 and pray to God that it works. Not so fast. Okay. Right, let's do some more praying. What? Let's see here. I think there's some kind of spacing issue. Feel like, oh right, so this needs to actually be, I haven't used these in a while, so I think it needs to be like this. Okay, while negative infinite is not return, why is it doing negative infinite? Oh, right. So this is a mistake here. So the problem is, if this is the case, then, yeah. So this is a mistake because this needs to be a maximum of res still. And then this needs to be like this. Yeah. Okay. There we go. And yeah, because I just had it just say return negative float infinity plus whatever this is, so it's always going to return negative infinity. All right, nice. Okay, and so we upped our efficiency a little bit with that optimization, so that's good to see. Okay, so let's think of the space and time complexity here. So the way this is going to be is this is going to be like a 2 to the n algorithm, right? Like it's going to be like a tree, and then every next level is going to double. And so for the time complexity here, it's going to be 2 to the, because we can either take the request or not, right? We have 2 choices in a backtracking in this case. And so let's think about like how many requests do we have and such, and like how far we have to go down. So this is going to be, if r is the request, I think it's 2 to the r. But we do have to do one more thing. So we are going to take requests, right? Like we're going to take requests. This is going to keep doubling, or whatever. But once we get to the base case where we're actually going to have the most number of items, like this will be over half the list. At every single one of these base cases, we actually have to check for the minimum or the maximum in the list at every single one, which is going to be the number of buildings. So every single one of these is going to take n time, and every single one of these is going to take constant time. But because the bottom level is more than half the list, we need to multiply by that as well. Now, once again, you could argue that this is, constant because n is only like 16, which is totally fine. So if you wanted to say that since n is only 20, this is just a constant time thing, totally fine. We can leave it like that. In fact, I'd probably say that is the case. But I'd still talk about it. Okay, and for the space, so let's think about this. So the space, we are making this net request, which is n. Once again, you can argue constant time. And we have to also think about the recursive call stack for this turtle speed thing. And the nice thing is because these arguments are so small, right? So we're going through every request, so that would, the most requests you can have is r. So it would be n plus r, but because they're only 20 and 16, could argue constant time as well. Small variables. So, okay. So that's going to be it for this problem. Hopefully you liked it, and if you did, please like the video and subscribe to the channel, and I will see you in the next one. Thanks for watching.